Hello there, and welcome to the Sleepy Library. Tonight, we are floating into the vast, quiet realm of space, where mysteries unfold across distances beyond imagination, and time moves in ways that challenge everything we think we understand. The universe is not just a backdrop for our existence. It is a living story written in light and darkness, in gravity and motion, in particles too small to see and structures too large to comprehend. Out there, beyond our atmosphere, beyond our solar system, beyond our galaxy, are wonders that defy simple explanation, yet follow elegant laws. This evening, we will wander through the cosmos together, exploring facts that soothe the mind with their gentle strangeness. Each truth we encounter is real, verified by instruments and observation, yet each carries a quality of dream. If you enjoy these quiet journeys into knowledge, I invite you to like, subscribe, or share a thought below. It helps others find their way here, one sleepy soul at a time. But for now, let your breath slow, let your shoulders drop. Allow the weight of the day to settle. Let us begin our gentle voyage through the endless quiet of space. Space is almost entirely empty, yet it contains everything we know. When we think of the universe, we often imagine stars, planets, and galaxies packed densely together. But the reality is far more humbling. The vast majority of space is void, a near-perfect vacuum where matter is so scarce that you could travel for thousands of miles without encountering a single atom. Between galaxies, the emptiness is even more profound. In these intergalactic regions, there might be just one hydrogen atom per cubic meter. On Earth, by contrast, a cubic meter of air at sea level contains approximately 27,000 trillion molecules. The universe is mostly nothingness, punctuated by tiny islands of matter and energy. Yet within this emptiness, everything that matters to us exists. Every star that lights the night, every world that orbits, every particle that could someday form life. The void is not truly empty. It seethes with quantum fluctuations, where particles pop into existence and vanish again in fractions of a second. The vacuum hums with invisible energy, with fields that permeate all of space, connecting everything to everything else in ways we are only beginning to understand. This emptiness is the canvas upon which the universe paints its story. And somehow, in all that nothing, there is room for wonder. The universe is constantly expanding, carrying galaxies away from each other. When astronomers first discovered that distant galaxies were receding from us in every direction, they realized something extraordinary. The universe itself is growing larger. Space is not a fixed stage on which cosmic objects move. Space itself stretches, like the surface of an inflating balloon. As it expands, galaxies move apart, not because they are traveling through space, but because the space between them is increasing. This expansion is happening everywhere, all at once. Every region of the universe is growing more distant from every other region. And remarkably, this expansion is accelerating. Something called dark energy, which makes up approximately 68% of all the energy in the universe, is pushing space to expand faster and faster. We do not know what dark energy is. We cannot see it or touch it. We can only observe its effects as galaxies rush away from us at ever-increasing speeds. In the far future, billions of years from now, This acceleration will carry distant galaxies beyond our observable horizon. Their light will be stretched so thin that it will never reach us. The universe will appear lonelier, darker, as if each galaxy were an island disappearing into a fog that can never be crossed. But for now, we can still see them. We can still map the Great Recession, watching as light from distant worlds tells us they are moving away, pulled by forces we barely comprehend. Time moves differently depending on where you are and how fast you are moving. This is one of the most beautiful and strange truths about the universe. Time is not a river that flows the same for everyone. It is flexible, malleable, affected by gravity and motion. The stronger the gravity you experience, the slower time passes for you compared to someone in weaker gravity. This phenomenon, called gravitational time dilation, has been measured with extraordinary precision. Clocks on GPS satellites, which orbit high above Earth where gravity is slightly weaker, tick faster than identical clocks on the ground. Without correcting for this effect, GPS systems would accumulate errors of several miles per day. Even more dramatically, if you could stand on the surface of a neutron star, where gravity is millions of times stronger than on Earth, time would pass much more slowly for you than for an observer far away. If you spent 1 hour on that neutron star and then returned to space, you might find that years had passed elsewhere. Near a black hole, this effect becomes extreme. Close to the event horizon, time slows so much that to a distant observer, you would appear almost frozen, your movements stretched out over years, decades, centuries. Yet from your own perspective, time would feel normal. You would not notice anything unusual. This is the deep strangeness of relativity. Time is personal. It depends on your path through the universe. There is no universal clock that ticks the same for everyone. Each of us experiences our own time, shaped by where we are and how we move. The cosmic web is the largest structure in the universe. On the grandest scales, the distribution of matter is not random. Galaxies are not scattered like seeds thrown carelessly across space. They are organized into an intricate network of filaments, sheets, and voids that resembles a vast spiderweb stretching across the cosmos. This structure, known as the cosmic web, is composed primarily of dark matter, an invisible substance that makes up approximately 85% of all matter in the universe. Dark matter does not emit light, but we can detect its presence through its gravitational effects. It forms the scaffolding of the universe, the hidden architecture that holds everything together. Along the filaments of this web, galaxies form and evolve. Gas flows through these channels like rivers, feeding star formation and building worlds. At the intersections of filaments, where multiple strands meet, enormous clusters of galaxies gather. These clusters are the densest regions of the cosmic web, containing hundreds or thousands of galaxies bound together by gravity. Between the filaments lie voids, vast regions where almost nothing exists. These voids can span hundreds of millions of light years, containing only a handful of galaxies scattered across enormous emptiness. The cosmic web formed slowly over billions of years, as gravity pulled matter together along preferred directions. In the early universe, tiny variations in density grew over time. Regions that were slightly denser attracted more matter, becoming denser still. This process continued, amplifying small differences until they became the grand structures we see today. Recently, astronomers captured the first high-definition image of a cosmic filament, a strand of gas connecting two galaxies from when the universe was just 2 billion years old. The image shows diffuse hydrogen glowing faintly as it flows along the filament, confirming what simulations had predicted. The cosmic web is real, and it has been real for most of cosmic history. When you look up at the night sky, you are seeing a tiny corner of this grand structure. Our own galaxy, the Milky Way, sits within a filament connecting larger clusters. We are part of the web, suspended in its delicate threads, carried along by its slow, patient construction. Neutron stars are among the most extreme objects in the universe. When a massive star exhausts its fuel and can no longer support itself against gravity, its core collapses in a catastrophic event called a supernova. If the star was between about 8 and 25 times the mass of the Sun, what remains after this explosion is a neutron star. These objects are almost incomprehensibly dense. A neutron star packs roughly 1.5 times the mass of the Sun into a sphere only about 20 kilometers across. If you could bring a sugar cube of neutron star material to Earth, it would weigh about 1 trillion kilograms, equivalent to the mass of a mountain. The matter inside a neutron star is so compressed that protons and electrons are forced together to form neutrons. The entire star becomes, in a sense, one giant atomic nucleus. The density is so extreme that a marshmallow dropped onto the surface would impact with the force of 1,000 nuclear explosions. If you could stand on a neutron star, which you cannot, you would be crushed into a layer only a few atoms thick. Some neutron stars spin with extraordinary speed. As the core of a massive star collapses, conservation of angular momentum causes it to spin faster, like a figure skater pulling in their arms. The fastest known neutron stars rotate hundreds of times per second. These spinning neutron stars often have powerful magnetic fields, trillions of times stronger than Earth's field. The combination of rapid rotation and intense magnetism causes them to emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep through space like lighthouse beams. If one of these beams happens to point toward Earth, we detect regular pulses of radiation. These objects are called pulsars. The pulses are so regular that when they were first discovered, astronomers briefly wondered if they might be signals from intelligent civilizations. But the explanation is natural, a consequence of physics at its most extreme. Pulsars are among the most precise clocks in the universe. Their rotations are so stable that astronomers can use them to test fundamental theories of physics, including Einstein's theory of gravity. Observations of a pair of neutron stars orbiting each other provided the first indirect evidence for gravitational waves, ripples in space-time predicted by general relativity. Neutron stars reveal what matter becomes when pushed to its limits. They are laboratories for physics that cannot be replicated anywhere on Earth. They show us that the universe has not finished surprising us, that there are states of matter so alien that we are still learning how to describe them. Light from distant stars takes so long to reach us that we see the past. The universe is vast beyond comprehension, and light, though it travels faster than anything else we know, is still limited in speed. Light moves at approximately 300,000 kilometers per second. That seems impossibly fast by human standards. In 1 second, light could circle Earth more than 7 times. Yet across cosmic distances, even light becomes slow. The nearest star system to our Sun, Alpha Centauri, is about 4 light-years away. This means the light we see from it tonight left its surface 4 years ago. We are seeing Alpha Centauri as it was 4 years in the past. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years distant. When you look at Andromeda, you see it as it appeared 2.5 million years ago, when our ancestors were still walking across the African plains, learning to use tools. The light from the most distant galaxies we can observe has been traveling for more than 13 billion years. These galaxies appear to us as they were when the universe was young, only a few 100 million years after the Big Bang. They are long gone now, transformed by billions of years of evolution we cannot see. Their light carries messages from a cosmos that no longer exists in that form. This creates a peculiar truth. The farther we look into space, the farther we look into time. Our telescopes are time machines. They allow us to observe the history of the universe, written in light that has been traveling toward us for eons. Some of the stars you can see in the night sky no longer exist. They ended their lives long ago, perhaps collapsing into black holes or dispersing their material into space. But their light is still on its way to us, carrying the image of stars that have passed from existence. This is the universe's gentle patience. It does not erase its history. It sends it forward, preserved in the light that travels through the void, waiting to tell its story to whoever has the instruments to listen. Dark matter and dark energy dominate the universe, yet we cannot see them. Everything we can observe directly, all the stars and galaxies, all the planets and nebulae, all the light and radiation we can detect, makes up less than 5% of the total content of the universe. The remaining 95% is invisible, known to us only through its effects. About 27% of the universe consists of dark matter. This mysterious substance does not emit, absorb, or reflect light. It does not interact with electromagnetic radiation in any way we can detect. Yet, we know it exists because of its gravitational influence. Galaxies rotate faster than they should, based on the visible matter we can see. Something unseen must be providing additional mass to hold them together. Clusters of galaxies bend light passing nearby, an effect called gravitational lensing. The amount of bending indicates far more mass than we can account for with visible matter alone. Dark matter is not a single substance, but possibly several exotic particles that interact weakly with ordinary matter. Scientists are searching for these particles, using sensitive detectors deep underground, shielded from cosmic rays. So far, dark matter remains elusive, but its effects are everywhere. It forms the skeleton of the cosmic web. It shapes the distribution of galaxies. Without dark matter, the universe would look completely different. Even more mysterious is dark energy, which makes up approximately 68% of the universe. This strange form of energy is causing the expansion of space to accelerate. We discovered dark energy only in the late 1990s, when astronomers studying distant supernovae realized that the universe was not just expanding, but expanding faster over time. This was shocking. Scientists had expected gravity to slow the expansion. Instead, some unknown force was pushing space apart with increasing vigor. We call it dark energy, but the name tells us almost nothing. It could be a property of space itself, a fundamental energy density woven into the fabric of the vacuum. It could be something we have not yet imagined. What we know is that dark energy is winning. It is stronger than gravity on cosmic scales, and it is driving galaxies apart. In the far future, dark energy will dominate the universe even more completely. Galaxies will be isolated islands, each alone in an ever-expanding void. But these mysteries, dark matter and dark energy, remind us how much we do not know. The universe is larger and stranger than our current understanding. It holds secrets that may take generations to unravel. And that uncertainty, that vast unknown, is part of what makes space so captivating. Auroras are visual echoes of solar storms. On Earth, we are fortunate to witness one of space's most beautiful phenomena without leaving our planet. Auroras, known as the northern lights in the Arctic and the southern lights in the Antarctic, are shimmering curtains of light that dance across polar skies. They appear in shades of green, red, blue, and purple, undulating and shifting as if alive. Their beauty has inspired human wonder for millennia. The Inuit peoples of Alaska call them Kiuuyat. Ancient European observers saw them as omens or spirits. But we now understand their origin, and the explanation is as wondrous as the sight itself. Auroras begin with the sun. Our star constantly emits a stream of charged particles, primarily electrons and protons, called the solar wind. This wind flows outward in all directions at speeds of hundreds of kilometers per second. Occasionally, violent events on the sun's surface, such as solar flares or coronal mass ejections, hurl enormous clouds of plasma into space at even higher speeds. When these energetic particles reach Earth, they encounter our magnetosphere, the protective magnetic field that surrounds our planet. Most particles are deflected around Earth, like water flowing around a rock in a stream. But some particles are funneled along magnetic field lines toward the north and south poles. As these particles descend into the upper atmosphere, they collide with atoms and molecules of oxygen and nitrogen. These collisions transfer energy to the atmospheric particles, exciting them to higher energy states. When the excited particles return to their normal state, they release this energy as light. The color of the aurora depends on which atmospheric particles are involved and at what altitude the collisions occur. Green auroras, the most common, result from oxygen molecules at altitudes between 100 and 300 kilometers. Red auroras, rarer and fainter, come from oxygen at higher altitudes, above 300 kilometers. Blue and purple hues arise from nitrogen. The auroras are dynamic because the solar wind is never constant. It buffets Earth's magnetosphere irregularly, strengthening and weakening, creating waves and ripples in the magnetic field. These fluctuations cause the auroral lights to shift and shimmer. During particularly strong geomagnetic storms, auroras can be seen much farther from the poles than usual. In extreme events, they have been observed as far south as the Caribbean. Auroras are not unique to Earth. Any planet with a magnetic field and an atmosphere can experience them. Jupiter and Saturn have auroras far more powerful than Earth's, driven by their immense magnetic fields. Even some distant stars have been found to produce auroral emissions. These lights are reminders that we are connected to the Sun, that our planet exists within the Sun's extended atmosphere. Space weather, the term for variations in the solar wind and magnetic storms, affects us in subtle ways. It can disrupt satellite communications, interfere with GPS navigation, and create electrical currents in power lines. But it also gives us the auroras, one of nature's most magnificent displays, a visual echo of the sun's restless energy reaching out to touch our world. The universe was born in an event we call the Big Bang. Approximately 13.8 billion years ago, all the matter and energy in the universe, all of space and even time itself, erupted into existence. This was not an explosion in space, it was an explosion of space. There was no before the Big Bang in any conventional sense, because time itself began with this event. In the earliest moments, the universe was unimaginably hot and dense. It was a roiling plasma of fundamental particles, too energetic for atoms to form. As the universe expanded and cooled, conditions changed rapidly. Within the first few minutes, protons and neutrons combined to form the nuclei of the lightest elements, primarily hydrogen and helium. After about 380,000 years, the universe cooled enough for electrons to combine with these nuclei, forming the first neutral atoms. At this moment, light could finally travel freely through space. Before this, the universe had been opaque, so dense with charged particles that light could not travel more than a short distance without being scattered. But once atoms formed, the universe became transparent. This ancient light, stretched and cooled by billions of years of cosmic expansion, still fills the universe. We can detect it as the cosmic microwave background, a faint glow coming from every direction in the sky. It is the oldest light in the universe, a snapshot of the cosmos as it appeared just a few 100,000 years after the Big Bang. The cosmic microwave background is remarkably uniform, with only tiny variations in temperature from place to place. These variations, less than 1 part in 100,000, were the seeds of all structure in the universe. Regions that were slightly denser than average had slightly more gravity, attracting more matter. Over millions and billions of years, these tiny differences grew into the galaxies, stars, and planets we see today. The Big Bang theory is supported by multiple lines of evidence. The expansion of the universe, predicted by the theory and confirmed by observations, shows that everything was once closer together. The abundance of light elements matches what the theory predicts should have formed in the early universe. The cosmic microwave background radiation is exactly what we would expect from a young, hot, dense universe that has since cooled and expanded. Understanding the Big Bang does not answer every question. We do not know what, if anything, came before it. We do not know why the Big Bang happened. We do not know if our universe is the only one. These questions remain open, invitations to future generations of scientists. But we do know that the universe has a history, a story that began in fire and has been unfolding ever since. Every atom in your body, every particle of oxygen you breathe, every element heavier than hydrogen and helium, was forged inside stars or in the violent explosions that marked their endings. You are made of stardust, quite literally. The universe created you. And now, billions of years later, you are here, contemplating the story of your own origin. Black holes are regions of space-time where gravity becomes infinite. When a very massive star reaches the end of its life and its core collapses, if there is enough mass remaining, nothing can stop the collapse. The matter compresses into a point of infinite density called a singularity. Around this singularity is a boundary called the event horizon. This is the point of no return. Anything that crosses the event horizon, including light itself, can never escape. From outside, we cannot see what happens inside a black hole. The event horizon is a one-way membrane, allowing things to fall in, but permitting nothing to come out. This makes black holes among the darkest objects in the universe. They do not emit light. They absorb everything, even the light that falls upon them. We can only detect black holes indirectly by observing their effects on nearby matter. If a black hole is part of a binary system with a normal star, it can pull gas from its companion. As this gas spirals toward the black hole, it heats up through friction and emits intense radiation, primarily in X-rays. By studying this radiation, we can infer the presence of the black hole. Some black holes are truly massive. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole containing millions or even billions of times the mass of the Sun. The black hole at the center of the Milky Way, called Sagittarius A star, has a mass of about 4 million suns. These supermassive black holes play an important role in galactic evolution. They influence the motion of stars and gas near the galactic center. When material falls into them, they can power enormous emissions of energy, creating some of the brightest objects in the universe, called quasars. The environment near a black hole is extreme in every way. Time dilation becomes so severe that an outside observer would see an object falling toward the event horizon slow down asymptotically, never quite reaching it, frozen in time at the edge of the abyss. Meanwhile, from the perspective of the falling object, time continues normally, and it crosses the event horizon in finite time, experiencing nothing unusual at the moment of crossing. Tidal forces near a black hole are immense. If you fell toward a black hole feet first, the difference in gravitational pull between your feet and your head would become so large that you would be stretched like taffy, a process gruesomely but accurately called spaghettification. For smaller black holes, this stretching would occur outside the event horizon. For supermassive black holes, the event horizon is so far from the singularity that tidal forces at the horizon are relatively mild, and you could cross it without immediate harm. But once inside, there is no escape. All paths lead inexorably to the singularity. Black holes are not eternal. Stephen Hawking showed that through quantum effects near the event horizon, black holes can slowly emit radiation and lose mass over time. This process, called Hawking radiation, is extraordinarily slow for large black holes, but becomes faster as they shrink. Over unimaginable spans of time, far longer than the current age of the universe, black holes will evaporate completely, leaving nothing behind but faint radiation. Black holes represent the ultimate triumph of gravity. They are places where the laws of physics as we understand them break down. They challenge our theories and force us to confront the limits of our knowledge. Yet they are not just theoretical curiosities. They exist throughout the universe, silent and patient, pulling in matter and light, shaping the cosmos in ways both subtle and profound. The speed of light is the ultimate speed limit of the universe. Nothing can travel faster than light in a vacuum. This is not just a practical limitation of current technology, it is a fundamental law of physics. The speed of light, approximately 300,000 kilometers per second, is woven into the structure of space-time itself. As an object with mass accelerates, it requires more and more energy to continue accelerating. As it approaches the speed of light, the energy required approaches infinity. No finite amount of energy can push a massive object to light speed. Only particles without mass, like photons, can travel at exactly the speed of light. This speed limit has profound consequences. It means that information cannot travel faster than light. If something happens on a distant star, we cannot know about it until light, or some other signal, crosses the intervening space. The universe has a built-in delay, a buffer between cause and effect that grows with distance. It also means that simultaneity is relative. Events that appear simultaneous to one observer may not appear simultaneous to another observer moving at a different velocity. The concept of now is not universal. Each observer has their own definition of the present moment, shaped by their motion through space-time. The constancy of the speed of light led Einstein to his theory of special relativity. Realized that if light always travels at the same speed, regardless of the observer's motion, then time and space must be flexible. They must adjust to keep the speed of light constant. This insight revolutionized physics and changed our understanding of the cosmos. Interstellar travel is hindered by this limit. Even at the speed of light, it would take years to reach the nearest stars, and tens of thousands of years to cross our own galaxy. For human explorers, this poses enormous challenges. Time dilation offers a partial solution. If you could travel at speeds very close to the speed of light, time would pass more slowly for you than for those left behind. You could cross vast distances while experiencing only a few years subjectively. But from Earth's perspective, decades, centuries, or millennia would have passed. You would arrive in the future, unable to return to the world you left. Some have speculated about ways to circumvent the light speed limit. Wormholes, hypothetical tunnels through space-time, could potentially connect distant regions without requiring faster-than-light travel. Warp drives, which would compress space in front of a ship and expand it behind, might allow effective faster-than-light motion without violating relativity. But these ideas remain speculative, requiring exotic forms of matter and energy that may not exist. For now, the speed of light remains an absolute barrier. It defines the structure of causality, the relationship between events, the very shape of the knowable universe. It is a limit, but it is also a guide, showing us that the universe has rules, deep and immutable, that govern everything from the smallest particles to the largest structures. There are more stars in the universe than grains of sand on all Earth's beaches. This comparison has become famous, and for good reason. It captures the staggering scale of the cosmos in terms we can almost grasp. Our galaxy, the Milky Way, contains between 100 billion and 400 billion stars. That is already an incomprehensible number. If you tried to count them at one per second, it would take thousands of years to count the stars in our galaxy alone. But the Milky Way is only one galaxy among countless others. Astronomers estimate there are approximately 2 trillion galaxies in the observable universe. Each of these galaxies contains millions, billions, or even trillions of stars. When you multiply these numbers together, you arrive at a total of roughly 10 to the 24th power stars in the observable universe. That is a 1 followed by 24 zeros. By comparison, estimates suggest there are roughly 7.5 times 10 to the 18th power grains of sand on all the beaches and deserts on Earth. That is a staggering amount of sand, more than most people could ever imagine. But it is still only a tiny fraction of the number of stars. The universe contains hundreds of times more stars than there are grains of sand on our entire planet. Each of those stars is a sun, potentially with its own system of planets, moons, asteroids, and comets. Each represents an entire world of possibilities, a unique story of formation and evolution. Some stars are larger than our sun, blazing with brilliant intensity and ending their lives in spectacular supernovae. Others are smaller, cooler, sipping their fuel slowly and shining steadily for trillions of years. And around many of these stars orbit planets. Recent discoveries have shown that planets are common throughout the galaxy. Most stars have at least one planet, and many have multiple planets. If even a tiny fraction of these worlds have conditions suitable for life, the number of potentially habitable planets is staggering. This abundance is both humbling and awe-inspiring. It suggests that we are not alone in any meaningful sense. The universe is too vast, too full of possibilities. Somewhere out there, around one of those countless stars, there may be other worlds where life has taken hold, where evolution has followed its own unique path, where perhaps beings look up at their own night sky and wonder if they are alone. But it also reminds us of our smallness. Earth is one planet among trillions upon trillions. Our sun is one star among an uncountable multitude. We are a whisper in a cacophony, a single note in an endless symphony. Yet here we are, capable of contemplating all of this. We have built telescopes and sent probes into space. We have measured distances to galaxies billions of light years away. We have counted stars, mapped structures, and begun to understand the grand architecture of the cosmos. That capacity for understanding is itself a wonder, perhaps as remarkable as the vast universe we study. Planets exist in astonishing variety throughout the galaxy. For most of human history, the only planets we knew were those in our own solar system. They provided our templates for what a planet could be: rocky worlds like Earth and Mars, gas giants like Jupiter and Saturn, ice giants like Uranus and Neptune. But as technology improved, and we began detecting planets around other stars, we discovered that our solar system is not typical. The galaxy is filled with planets far stranger than anything we imagined. There are hot Jupiters, gas giants that orbit their stars in just a few days, so close that their atmospheres are heated to thousands of degrees. These worlds should not exist according to early theories of planet formation. Gas giants are thought to form far from their stars, where volatile materials can condense. But somehow, hot Jupiters migrated inward, spiraling closer to their suns over millions of years. They orbit so near that their year is shorter than our week. Some are slowly evaporating, their outer atmospheres blown away by intense stellar radiation. There are super-Earths, rocky planets larger than Earth but smaller than Neptune. We have nothing like them in our solar system, yet they are among the most common types of exoplanets. We do not know what they are like. Are they scaled-up versions of Earth, with thick atmospheres and possible oceans? Or are they mini-Neptunes, with deep atmospheres of hydrogen and helium surrounding small, rocky cores? Future observations will help answer these questions. There are rogue planets, worlds that do not orbit any star. These planets were either ejected from their birth systems by gravitational interactions or formed independently in the darkness of interstellar space. They wander the galaxy alone, illuminated only by the faint glow of distant stars. Without a sun to warm them, they are cold and dark. But beneath thick, insulating atmospheres or icy crusts, some might retain internal heat from their formation or from radioactive decay. In theory, such worlds could even harbor subsurface oceans, kept liquid by geothermal warmth. There are planets around binary stars, worlds that orbit two suns like something from science fiction. The sky on such a planet would feature twin suns, rising and setting, casting double shadows. The climate would be strange, modulated by the complex dance of two stellar partners. During certain seasons, both suns might be in the sky together. During others, only one might shine, or they might eclipse each other, plunging the world into temporary twilight. There are planets made primarily of carbon rather than silicates. These carbon planets might have surfaces of graphite or diamond, with skies filled with carbon-based hazes. There are ocean worlds, planets entirely covered in deep water, with no land anywhere. There are lava worlds, where the surface is a molten sea of rock, kept liquid by extreme proximity to their stars. The diversity of planets is almost infinite. Each star system is an experiment in world building, shaped by the mass and composition of the protoplanetary disk, by the dynamics of formation, by the influence of nearby stars or passing clouds of gas. No two systems are quite alike. This variety suggests that the processes of planet formation are robust but flexible. Planets can form under a wide range of conditions, adapting to the circumstances of their birth. And it means that when we eventually study these worlds in detail, we will find climates, chemistries, and possibly even biologies that we never anticipated. The universe is more creative than we are. Gravity shapes everything on cosmic scales. Gravity is the weakest of the four fundamental forces of nature. On small scales, it is easily overpowered by electromagnetic forces, which are vastly stronger. The electromagnetic force holding atoms together is many orders of magnitude more powerful than the gravitational attraction between those same atoms. Yet on cosmic scales, gravity dominates. It is the force that shapes galaxies, clusters of galaxies, and the entire large-scale structure of the universe. Gravity is unique among the forces because it is always attractive and because it has unlimited range. Every particle of matter exerts a gravitational pull on every other particle, no matter how distant. Over large distances and with large amounts of mass, these individual attractions add up to immense forces. Gravity pulled together the first clouds of hydrogen gas in the early universe, compressing them until temperatures and pressures became high enough for nuclear fusion to ignite. The first stars were born from gravity's patient accumulation. Gravity gathered these stars into galaxies and gathered galaxies into clusters. It sculpted the cosmic web, creating filaments and voids. Gravity holds planets in orbit around stars and moons in orbit around planets. It shapes stars themselves, balancing the inward pull of gravity against the outward pressure of fusion. When fusion stops, gravity takes over completely, collapsing stellar cores into white dwarfs, neutron stars, or black holes. Gravity bends light. According to Einstein's theory of general relativity, massive objects curve space-time, and light follows the contours of this curved space. This effect, called gravitational lensing, allows us to observe distant galaxies that lie behind massive clusters. The cluster acts as a cosmic magnifying glass, bending and amplifying the light from background galaxies. Some of the most distant galaxies ever observed were detected this way, their light focused by the gravity of intervening matter. Gravity creates tides. On Earth, we experience tides as the rise and fall of ocean waters, caused primarily by the Moon's gravity, and to a lesser extent by the Sun's gravity. These tides are gentle reminders of gravitational forces at work. But in more extreme environments, tidal forces can be violent. A moon orbiting too close to a planet can be torn apart by tidal forces, the difference in gravitational pull between its near and far sides exceeding the moon's own gravity. The resulting debris forms a ring around the planet. Saturn's magnificent rings may have formed this way. Gravity is also responsible for the phenomenon of gravitational waves. When massive objects accelerate, particularly when they orbit each other closely, they create ripples in space-time that propagate outward at the speed of light. These waves were predicted by Einstein, but not detected until 2015, when instruments finally became sensitive enough to detect the tiny distortions caused by waves from two merging black holes. Since then, dozens of gravitational wave events have been detected, opening a new window on the universe. Despite its dominance on large scales, gravity remains the most mysterious force. We do not have a complete quantum theory of gravity. We do not fully understand how gravity behaves at the smallest scales or in the most extreme conditions near singularities. Reconciling gravity with quantum mechanics is one of the great unsolved problems in physics. But we do know that gravity is fundamental. It is the force that holds the universe together, that structures matter from planets to superclusters, that shapes the geometry of space-time itself. Understanding gravity is essential to understanding the cosmos. Space is filled with radiation invisible to our eyes. When we look at the night sky, we see only a narrow slice of the electromagnetic spectrum. Our eyes are sensitive to visible light, wavelengths between about 400 and 700 nanometers. This is a tiny fraction of the full spectrum of electromagnetic radiation. The universe emits light at all wavelengths, from long radio waves to short, energetic gamma rays. Each wavelength reveals different aspects of the cosmos. Radio waves, the longest wavelengths, can pass through dust and gas that block visible light. Radio telescopes allow us to see into dense molecular clouds where stars are forming, hidden from optical view. The supermassive black hole at the center of our galaxy, obscured by intervening dust, was imaged using radio waves. Pulsars, rapidly rotating neutron stars, emit powerful beams of radio waves that sweep across space. Infrared radiation, with wavelengths just longer than visible light, reveals heat. Cool objects that do not emit much visible light can glow brightly in infrared. This allows us to study cold dust, brown dwarfs, and the surfaces of planets shrouded by thick atmospheres. Infrared observations can also penetrate dust, revealing young stars embedded in their birth clouds. Ultraviolet radiation, with wavelengths just shorter than visible light, is emitted by hot objects. The hottest, most massive stars shine brightly in ultraviolet. Ultraviolet telescopes can map the regions of active star formation in distant galaxies, tracing the birth of stellar populations. X-rays are emitted by extremely hot gas and by matter falling into black holes and neutron stars. X-ray observations reveal the violent side of the universe. Supernova remnants, where stars have exploded and left behind shells of hot, expanding gas, glow brightly in X-rays. Clusters of galaxies contain enormous reservoirs of hot gas, heated by gravitational collapse and visible only in X-ray light. Gamma rays, the shortest and most energetic wavelengths, are produced by the most violent events in the universe. Gamma ray bursts, brief flashes of gamma rays lasting from milliseconds to minutes, are thought to be produced by the collapse of massive stars or the mergers of neutron stars. These events release as much energy in a few seconds as the Sun will emit over its entire lifetime. By observing the universe at multiple wavelengths, astronomers build a more complete picture of cosmic phenomena. A supernova remnant might appear as a faint shell in visible light, a bright arc in radio waves, a complex structure in X-rays, and a source of high-energy particles in gamma rays. Each wavelength adds information, revealing different physical processes at work. Space-based telescopes are essential for observing many of these wavelengths. Earth's atmosphere blocks most ultraviolet, X-ray, and gamma-ray radiation, protecting life on the surface, but preventing ground-based telescopes from detecting these wavelengths. Satellites orbiting above the atmosphere provide our only view of these high-energy realms. The invisible universe is just as rich and complex as the visible one. By expanding our vision beyond the narrow band our eyes can see, we have discovered a cosmos filled with phenomena we never imagined. From the coolest dust clouds to the hottest plasmas, from the gentlest radio whispers to the most violent gamma-ray shouts. Time near the beginning of the universe passed differently than it does now. The early universe was not just hotter and denser than today. Its very structure, including the passage of time, was different. In the first moments after the Big Bang, when the universe was unimaginably small and hot, quantum effects dominated. Space and time may not have existed as separate, well-defined entities. They may have been blurred together in a quantum foam, where the usual laws of physics broke down. As the universe expanded and cooled, time as we know it emerged. But the rate at which physical processes occurred changed over cosmic history. In the dense, hot, early universe, particles collided with immense frequency. Interactions that would take billions of years in the modern universe happened in fractions of a second. The first atoms formed only 380,000 years after the Big Bang. This sounds like a long time, but in that brief period, the universe underwent transformations that, in today's universe, would take far longer. Stars began forming a few 100 million years after the Big Bang. Galaxies assembled over the next several billion years. But the processes that formed these early stars and galaxies were different from those occurring now. The first stars, called population 3 stars, formed from pristine hydrogen and helium. They contained no heavier elements because none existed yet. These stars were likely far more massive than most stars today, burning brilliantly and briefly before exploding in supernovae that seeded space with the first heavy elements. The rate of star formation in the universe peaked when the universe was a few billion years old. This was a period of intense activity, often called the cosmic noon. Galaxies were forming stars at rates far higher than in the present day. The universe was brighter, more active, more violent. Since then, star formation has declined. The universe is running out of easily accessible gas to form new stars. Existing stars are slowly dying, and the rate of replacement is slowing. The universe is growing darker and quieter. In the far future, this trend will continue. Star formation will eventually cease entirely. Existing stars will age and fade. White dwarfs will cool to black dwarfs. Neutron stars will remain inert. Black holes will slowly evaporate through Hawking radiation. Trillions upon trillions of years from now, the universe will be a cold, dark place, filled with the remnants of once luminous objects, separated by ever-growing distances. Time will continue, but it will be a time of stillness. Yet even this distant future is not the end. In the unimaginable reaches of time, beyond even the evaporation of black holes, the universe might transition into a state we cannot yet describe, governed by physics we do not yet understand. Time itself might change meaning in ways we cannot foresee. The history of the universe is the history of time itself, and it is a story that is still being written. Spacecraft have left our solar system, carrying messages from humanity. In the 1970s, NASA launched 4 spacecraft designed to explore the outer planets: Pioneer 10 and 11, and Voyager 1 and 2. These missions were spectacularly successful. Voyager 2 remains the only spacecraft to have visited Uranus and Neptune. The images and data returned by these probes revolutionized our understanding of the giant planets and their moons. But the journeys of these spacecraft did not end with their planetary encounters. All 4 are now on trajectories that will carry them out of the solar system entirely. They are becoming interstellar spacecraft, venturing into the space between stars. Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to interstellar space, in 2012. Voyager 2 followed in 2018. They are now traveling through the interstellar medium, the thin gas that fills the space between stars. They continue to send back data, though their power sources are slowly failing. Eventually, within the next decade or so, they will fall silent. But even without communication, they will continue their journeys. Both Voyager spacecraft carry a golden record, a phonograph record containing sounds and images, selected to represent the diversity of life and culture on Earth. The record includes greetings in 55 languages, music from various cultures and eras, natural sounds like thunder and birdsong, and encoded images showing scenes from Earth. The golden records were intended as messages to any intelligent beings who might one day encounter the spacecraft. The chances of such an encounter are vanishingly small. Space is vast, and the Voyagers are traveling at only a few kilometers per second relative to nearby stars. It will take tens of thousands of years for them to pass anywhere near another star system. Even then, the likelihood of being found is minuscule. But the records were not really about communication with extraterrestrials. They were about communicating with ourselves. The golden records are time capsules, messages sent from humanity in the late 20th century to whoever might exist in the distant future. They are expressions of hope and curiosity, artifacts of a species that looked outward and wondered what else might be out there. The pioneers carried plaques with similar intent, showing the location of Earth relative to nearby pulsars and depicting a man and woman. These spacecraft, now silent or soon to be, will wander the galaxy for millions or billions of years. Long after human civilization has changed beyond recognition, these artifacts will remain, carrying traces of who we were, what we valued, and what we dreamed. They are among the most enduring things humanity has ever created. The universe contains structures on scales we can barely comprehend. We have already discussed the cosmic web, the largest known structure in the universe. But within this web, there are individual structures that dwarf anything we encounter in daily life. Galaxy clusters, the largest gravitationally bound structures, can contain hundreds or thousands of galaxies. The Coma cluster, for example, contains over 1,000 identified galaxies. These galaxies are not distributed randomly, but are embedded in an enormous halo of dark matter. The cluster also contains vast quantities of hot gas, heated to millions of degrees by the gravitational potential of the cluster. This gas emits X-rays and constitutes a significant fraction of the cluster's ordinary matter. Some galaxy clusters are arranged into even larger structures called superclusters. The Virgo supercluster, which contains our own Milky Way, includes the local group of galaxies, the Virgo cluster, and numerous smaller groups and clusters, all loosely connected by gravity. The Virgo supercluster spans about 110 million light-years. But superclusters are not the end. Recent mapping efforts have identified structures called galaxy filaments and walls that stretch across hundreds of millions of light-years. The Sloan Great Wall, discovered in 2003, is a vast concentration of galaxies stretching over 1.3 billion light-years. The Hercules Corona Borealis Great Wall, even larger, spans approximately 10 billion light-years, though its designation as a single structure is debated. These immense structures formed from the gravitational collapse of matter along preferred directions in the early universe. They are the echoes of quantum fluctuations in the first moments after the Big Bang, amplified over billions of years into the largest patterns in the cosmos. At the other extreme, the universe contains structures of exquisite delicacy and detail. Planetary nebulae, the glowing shells of gas ejected by dying stars, exhibit intricate shapes shaped by magnetic fields, stellar rotation, and binary companions. Some resemble butterflies, others rings, still others elaborate spirals. Each is unique, a final work of art created by a star at the end of its life. Supernova remnants, expanding shells of debris from exploded stars, create vast bubbles of hot gas. Over thousands of years, these remnants grow and fade, enriching the interstellar medium with heavy elements. Star-forming regions, like the Eagle Nebula or the Carina Nebula, are enormous clouds of gas and dust, where gravity is sculpting new stars. Within these nebulae, Dense cores collapse under their own weight, heating up until fusion ignites. The newly born stars emit intense radiation that blows away surrounding gas, revealing themselves to our telescopes. From the smallest grains of interstellar dust to the largest superclusters, the universe exhibits structure at every scale. Each level reveals new patterns, new physics, new beauty. And at every scale, we find that the universe is not chaotic. It is organized, governed by laws that apply universally, creating patterns that we can study, understand, and appreciate. Life on Earth relies on the specific conditions of our planet, but the ingredients for life are widespread. Carbon, the backbone of organic chemistry, is one of the most abundant elements in the universe. It is forged in the cores of stars through nuclear fusion and dispersed into space when stars exhale gas or explode. Oxygen, essential for many forms of life on Earth, is also abundant, formed in massive stars and scattered by supernovae. Nitrogen, hydrogen, sulfur, phosphorus, all the elements necessary for life as we know it, are common throughout the cosmos. Water, that most essential molecule, is everywhere in space. It exists as ice in comets and on distant moons. It has been detected as vapor in the atmospheres of exoplanets. Vast clouds of water vapor have been found orbiting distant quasars, containing more water than exists in all of Earth's oceans combined. The building blocks of life are not rare. They are universal. Amino acids, the components of proteins, have been found in meteorites that fell to Earth. Complex organic molecules have been detected in interstellar clouds. The chemistry that underlies biology appears to be a natural consequence of the laws of physics and chemistry, occurring wherever conditions allow. This raises a profound question. If the ingredients for life are common, is life itself common? We do not yet know. Earth is the only place where we have confirmed the existence of life. But the discovery of thousands of exoplanets, many in the habitable zones of their stars where liquid water could exist, suggests that opportunities for life are plentiful. Some of these worlds may have conditions similar to Earth. Others may be very different, but still capable of supporting life in forms we have not yet imagined. Life on Earth thrives in extreme environments. Microbes have been found in boiling hot springs, in ice kilometers below the surface, in acidic lakes, in the deep ocean near volcanic vents where sunlight never reaches. Life is remarkably adaptable. It finds a way in almost any environment where liquid water exists and where there is a source of energy. This adaptability suggests that life might arise in places we once thought inhospitable. Beneath the icy crust of Jupiter's moon Europa, there may be a vast ocean kept liquid by tidal heating. Similar oceans might exist under the surfaces of Saturn's moon Enceladus and Neptune's moon Triton. These hidden oceans, warmed by internal heat rather than sunlight, could potentially harbor life. Mars, now cold and dry, once had liquid water on its surface. Rivers flowed, lakes formed, and perhaps life emerged. We do not know if Martian life ever existed, but the possibility is tantalizing. Missions to Mars are searching for signs of past or present life, drilling into rocks and analyzing soil. Venus, despite its hellish surface conditions, might have had oceans early in its history. Some scientists have even speculated that microbial life could exist in Venus's clouds, where temperatures and pressures are more moderate. The search for life beyond Earth is one of the most profound scientific endeavors of our time. It is not just a search for microbes or signals from distant civilizations. It is a search for understanding our place in the cosmos. Are we alone, a unique accident in a vast, indifferent universe? Or are we part of a larger community of life, one of countless worlds where evolution has crafted its own unique solutions to the challenges of existence? We do not yet have the answer, but we are looking, and the fact that we are looking, that we have the tools and the curiosity to ask these questions, is itself a remarkable thing. The concept of infinity appears in many aspects of the universe. Is the universe infinite? This is one of the oldest and most profound questions in cosmology. The observable universe, the portion of the universe from which light has had time to reach us, is finite. It has a radius of approximately 46 billion light-years, a distance set by the age of the universe and the expansion of space. We cannot see beyond this horizon, but the universe itself may extend far beyond what we can observe. If the universe is flat or open, as current observations suggest, it could be infinite in extent. Beyond our observable horizon, there would be more galaxies, more stars, more space, extending forever in all directions. In an infinite universe, every possible arrangement of matter would occur somewhere. There would be regions identical to our own, down to the smallest detail. There would be infinite copies of Earth, of you, of every moment in history. This is a dizzying thought, difficult to grasp. But it follows logically from the mathematics of an infinite universe. We do not know if the universe is truly infinite. Observations can only tell us about the observable portion. But the possibility of infinity opens philosophical questions. If the universe is infinite, does it contain everything that could possibly exist? Are there limits to what can happen? Or does infinity allow for all possibilities? Time may also be infinite. The universe had a beginning, the Big Bang, but it may have no end. The expansion of the universe is accelerating, and current models suggest this acceleration will continue forever. The universe will grow ever larger, ever colder, ever emptier, but it will not stop. Time will continue, infinite and unbounded. Within mathematics, infinity appears everywhere. Numbers extend infinitely in both directions. There are infinitely many points between any 2 points on a line. Infinity is a tool we use to describe and understand the world. But it is also a concept that challenges intuition. We cannot visualize infinity. We can only reason about it abstractly. Infinity reminds us that the universe is larger and stranger than our minds can fully encompass. It is a humbling thought, but also an exhilarating one. There is always more to discover, more to explore, more to understand. The boundaries of our knowledge are not walls, but horizons. And beyond every horizon lies another, and another, perhaps without end. The universe is governed by a small number of fundamental forces. Everything that happens in the cosmos, from the tiniest quantum interaction to the collision of galaxies, is governed by 4 fundamental forces. Gravity, which we have already discussed extensively, is the force that shapes large-scale structures. It is the weakest of the 4 forces, but dominates on cosmic scales because it is always attractive and has infinite range. Electromagnetism is far stronger than gravity on small scales. It is responsible for the structure of atoms and molecules, for chemical reactions, for the properties of light. Electromagnetic forces hold electrons in their orbits around nuclei. They bind atoms into molecules, and molecules into solids, liquids, and gases. Essentially, all of chemistry and biology is governed by electromagnetism. Light itself is an electromagnetic wave, a fluctuation in electric and magnetic fields propagating through space. The strong nuclear force binds protons and neutrons together inside atomic nuclei. Without this force, nuclei would fly apart, pushed by the electromagnetic repulsion between positively charged protons. The strong force is extremely powerful, but has a very short range, acting only over distances comparable to the size of a nucleus. It is the force that powers the Sun and all stars, holding nuclear fuel together and allowing fusion reactions to occur. The weak nuclear force is responsible for certain types of radioactive processes, including beta decay. It is weaker than electromagnetism and the strong force, but stronger than gravity. The weak force plays a crucial role in the Sun's energy production, enabling the fusion process that converts hydrogen into helium. These four forces govern everything. Every interaction, every process, every phenomenon in the universe arises from one or more of these forces. Understanding how they work and how they relate to each other is one of the central goals of physics. We have successfully unified electromagnetism and the weak force into a single theory called the electroweak force. We have theories, called quantum chromodynamics, that describe the strong force. But a complete unification of all four forces remains elusive. Gravity, described by general relativity, resists integration into the quantum framework that describes the other forces. Reconciling these theories is one of the great challenges of modern physics. If successful, such a theory would describe the universe at its most fundamental level, showing how all forces emerge from a single, unified framework. It would be the ultimate theory, a final answer to the question of how the universe works. But we are not there yet, and perhaps we will never arrive at a final theory. The universe may be more subtle than we imagine, revealing new layers of complexity as we probe deeper. Each answer may raise new questions. Each discovery may open new mysteries. The quest for understanding is ongoing, and it may be infinite. We are made of elements forged in stars. This is not poetic metaphor. It is literal truth. The hydrogen in your body, the most abundant element in the universe, was formed in the Big Bang, minutes after the universe began. But nearly every other element inside you has a different origin. Carbon, the foundation of organic chemistry, was created inside stars through nuclear fusion. In the cores of stars, where temperatures reach millions of degrees, hydrogen nuclei collide and fuse into helium. As stars age and conditions change, helium fuses into carbon. Oxygen, the element we breathe, was also formed in stars. Nitrogen, calcium, iron, all the elements heavier than helium, were forged in stellar furnaces. But for these elements to become part of us, they had to leave the stars where they were created. This happens in several ways. Some stars shed their outer layers gently, creating planetary nebulae that disperse enriched gas into space. Other stars end their lives in violent supernovae, explosions so powerful they briefly outshine entire galaxies. These explosions scatter elements across light years, seeding the interstellar medium with heavy elements. Over time, this enriched gas cools and condenses into new clouds. Gravity pulls these clouds together, forming new generations of stars, and around those stars, planets. Our solar system formed about 4.5 billion years ago from such a cloud, already enriched by previous generations of stars. The rocky planets, including Earth, are made primarily of elements forged in ancient stars. The iron in your blood, essential for transporting oxygen through your body, was created in a supernova billions of years ago. The calcium in your bones, the carbon in your DNA, the oxygen you breathe, all came from stars that lived and perished long before the sun was born. You are a collection of stardust, assembled over billions of years through the patient work of gravity and chemistry. This connection is profound. It means we are not separate from the universe. We are part of it, made of the same materials, governed by the same laws. The atoms in your hand were once inside a star. They have traveled across space and time, carried by stellar winds and shockwaves, incorporated into a planet, and eventually into living organisms. Every breath you take contains atoms that have been recycled through countless forms. Some of the carbon in your body was once in a dinosaur, a tree, a bacterium. Some of the oxygen you breathe was exhaled by a plant last week. The atoms are ancient, but their arrangements are temporary. When you pass, your atoms will return to the Earth and eventually to space. They will become part of new worlds, new stars, perhaps new forms of life. The cycle continues, endless and magnificent. We are the universe becoming aware of itself. We are stardust contemplating stars. And in that realization, there is a kind of peace, a sense of belonging to something vast and beautiful. Our understanding of the universe is always evolving. Everything written here represents our current understanding, built on observations, experiments, and theoretical work. But science is not static. It is a process of continuous refinement. Theories are tested, updated, and sometimes replaced. New observations challenge old assumptions. Technology advances, allowing us to see farther and more clearly. The history of cosmology is a history of surprises. We once thought the Milky Way was the entire universe. Then we discovered that the fuzzy nebulae in the sky were actually other galaxies, vastly distant. We thought the universe was eternal and unchanging. Then we discovered it had a beginning and is expanding. We thought the expansion was slowing. Then we discovered it is accelerating. Each of these discoveries revolutionized our understanding, and there will be more. Future telescopes will probe the early universe in greater detail, revealing the first stars and galaxies. They will study exoplanet atmospheres, searching for signs of life. They will map dark matter and test theories of gravity on cosmic scales. Experiments on Earth will search for dark matter particles, probe the properties of neutrinos, and test the limits of quantum mechanics. New generations of scientists will ask questions we have not yet thought to ask. They will develop theories we cannot yet imagine. The universe is full of mysteries waiting to be uncovered. What is dark energy? How did the first stars form? Are there other universes beyond our own? Is there life elsewhere in the cosmos? How do black holes work at their centers? Can we reconcile quantum mechanics and gravity? These questions, and countless others, drive the quest for knowledge. They keep us looking upward, outward, inward. They remind us that no matter how much we learn, there is always more. The universe is not a puzzle to be solved once and for all. It is a frontier, infinite and beckoning. And the act of exploring it, of seeking to understand, is one of the most noble endeavors of our species. In the face of a vast and ancient universe, we ask questions. We build instruments to extend our senses. We construct theories to make sense of what we observe. We share our findings, building on the work of those who came before us. This is humanity's gift to itself, the knowledge that we can know, that the universe is comprehensible, that by working together across generations, we can uncover its secrets. And when we do, we find not a cold mechanical clockwork, but a cosmos of staggering beauty, complexity, and wonder. The night sky connects us to everything that has ever been and ever will be. When you look up at the stars on a clear night, you are looking at history. The light from each star has traveled for years, decades, centuries, or millennia to reach your eyes. You are seeing these stars as they were, not as they are. The farther away a star, the further back in time you see. Some of the stars you can see with your naked eye are hundreds of light years away. The light you see tonight left those stars during the era of colonization on Earth, or the Renaissance, or the Middle Ages. If a star 500 light years away exploded yesterday, we would not know for another 500 years. The universe keeps its secrets, revealing them slowly as light makes its patient journey across space. But the night sky is also a window into the future. Every photon that enters your eye has traveled across the universe to reach you. It has passed through dust clouds and past distant galaxies. It has been redshifted by the expansion of space, carrying information about how the universe has changed. By studying starlight, astronomers can trace the history of the cosmos and predict its future. We know the sun will eventually exhaust its hydrogen fuel and swell into a red giant. We know that the Milky Way and Andromeda will collide in about 4 billion years, merging to form a larger galaxy. We know that stars will keep forming, living, and perishing for trillions of years, until the universe runs out of gas. We know that the universe will grow colder and darker, that galaxies will drift apart beyond our ability to reach them, that the stars will go out one by one until only silence remains. But these are events in the unimaginably distant future. For now, the universe is still vibrant, still full of light and motion, and we are here to witness it. The night sky is a gift, freely available to anyone who looks up. It does not require a telescope or an advanced degree. It only requires stillness, attention, and a sense of wonder. In the darkness, far from city lights, you can see the Milky Way, a glowing band arcing across the sky. That band is the combined light of billions of stars in our galaxy, too faint individually to resolve, but together forming a river of light. You are seeing your home from the inside, looking along the plane of the galactic disk. If you watch long enough, you might see a meteor, a fragment of an ancient comet burning up as it enters Earth's atmosphere. You might see a satellite, a human-made object reflecting sunlight as it orbits overhead. You might see the steady glow of a planet, Mars or Jupiter or Venus, wandering among the stars. Each sight connects you to something larger. The meteor is a remnant from the formation of the solar system, a piece of the same cloud that became the sun and planets. The satellite is a testament to human ingenuity, our ability to reach beyond our world. The planet is a companion, another world with its own history and mysteries. And the stars, those distant suns, are reminders that the universe is vast and full of possibilities. Somewhere out there, around one of those stars, might be another world where someone else is looking up at their own night sky, seeing our sun as a faint point of light, and wondering the same things we wonder. The night sky humbles us. It reminds us of our smallness. But it also elevates us, because in looking up, in asking questions, in seeking to understand, we participate in something timeless. Humans have always looked at the stars. Ancient peoples mapped the constellations, told stories about them, used them to navigate. Astronomers in ancient Greece, China, India, and the Middle East made careful observations and developed models of the heavens. Over centuries and millennia, our understanding has deepened, but the sense of wonder remains. When you look at the stars, you are connected to every human who has ever looked up and wondered. You are part of a long lineage of curiosity and exploration. And you are also connected to the cosmos itself, made of its materials, shaped by its laws, a product of its long, patient unfolding. The universe is not separate from you. You are part of it. And when you gaze at the night sky, the universe is looking at itself. Thank you for journeying with me tonight through the quiet vastness of space. We have wandered across distances that strain imagination, through time that stretches beyond memory, among objects so strange they challenge understanding. We have seen emptiness that is not empty, expansion that carries galaxies away, time that bends and slows, light that remembers what stars were long ago. We have touched the edges of the cosmic web, felt the pull of gravity across billions of light years, glimpsed the violence of supernovae and the serenity of ancient light. We have learned that we are made of stardust, that the atoms in our bodies were forged in furnaces we will never see, that our existence is woven into the fabric of the universe itself. And we have confronted the mysteries that remain, the questions we cannot yet answer, the frontiers that stretch endlessly before us. The universe is vast and we are small, but in our smallness we have found something remarkable: the capacity to understand. We have built telescopes that see across billions of light years. We have sent spacecraft beyond our solar system, carrying messages of hope. We have developed theories that describe the birth of the universe and predict its fate. We have asked questions and found answers, and each answer has led us to new questions, deeper and more profound. If you enjoyed this quiet exploration of space, I invite you to like, subscribe, or share a thought below. It helps other curious minds find their way here, one sleepy soul at a time, to share in the wonder of the cosmos. But for now, let all of that gently fade. Let your thoughts slow like distant galaxies receding into darkness. Let your breathing become as steady as the orbit of planets, ancient and sure. The universe is vast, and it will continue without you for a while. The stars will keep shining. The galaxies will keep turning. Time will keep flowing in its patient, inevitable way. You have done enough for today. You have looked upward and outward. You have contemplated distances and times beyond comprehension. You have held the universe in your mind, if only for a moment. And that is enough. Now let it all go. Close your eyes. Rest in the knowledge that you are part of something immense and beautiful. Rest in the quiet certainty that the universe knows you because you are made of it. Rest in the gentle embrace of infinity, knowing that there is always tomorrow to wonder again. Let sleep carry you across vast distances, through fields of stars and nebulae, past galaxies spinning in the dark. Let your dreams be filled with light. Good night.